Growing up, many of us played Angry Birds, pulling back a slingshot, aiming carefully, and hoping the projectile would hit its target. Our project brings that concept to life by transforming a familiar game mechanic into a measurable, data-driven engineering system. The objective is to create a projectile motion analysis platform that uses real-life data acquisition with kinematic modeling in LabVIEW. Our goal is to measure key physical parameters involved in projectile motion and use those measurements to validate projectile trajectories within a controlled experimental environment. Ultimately, this project demonstrates how instrumentation and computational modeling can work together to connect theoretical kinematics with measurable physical behavior.
Our first set of sensors will help us to track kinematic data in order for our system to make the necessary calculations for the projectile motion of our projectiles. First, we will have a potentiometer that will be placed along the loading mechanism of the launcher and will give our system the position of the launcher and the projectile. This will be done by having each draw length and launch angle send out a different voltage to our system. Next, we will have a velocity sensor that will be placed next to the launching mechanism in order to track the exit velocity of the projectile as it is released from the launcher. And then we will have a distance sensor that will be used to find how far the projectile travels. This may be done with either a force impact sensor that will track the impact of the projectile when it lands, or an ultrasonic sensor to pick up on the sound waves upon impact. For our next set of sensors, they will be used for weight classification. First, we will have a color sensor in order to differentiate the different colors between various targets and classes of projectiles. Different targets and projectiles will have varying colors based on their weight, and this will be tracked within our system in order so that we can put the weight in for our kinematic calculations. We will also have a weight sensor in the area where the projectile is placed before launching to ensure that the weight recorded in our system is accurate. For our more general sensors, we will have a webcam overhead of the system as a whole. This will track the positioning of targets and objects, as well as information on the projectile as it is launched and find its final position.
Building blocks for the project. Actuators for movement. The sensors being used will be the potentiometer, force impact sensor, motor control, and ultrasonic sensor. Transducer stage. A potentiometer will be used, which is a voltage divider output where voltage will change with ramp position. The force impact sensor, the impact force will result in a voltage spike. The motor control transfers signals to the motor through DAC voltage. The ultrasonic sensor transfers input and output signals through to track real-time object movement. Signal conditioning. Potentiometer contains a buffer amplifier that prevents any loading effects and maintains accurate voltage. The force impact sensor develops a circuit that is able to convert analog spikes into digital pulse for readability. Motor control. Current will be supplied to the motor through DAC signal control. Ultrasonic sensor tracks real-time pulses and converts signal into position. Data acquisition and readout. So the potentiometer, the voltage will go through a DAC VI channel and will be converted using a calibration line. The force impact sensor will detect impact force when it exceeds a set threshold. The motor control, DAC transfers user input into voltage output that shifts the angle. Ultrasonic sensor sends pulses which will read data back that is converted into position using various DAC channel types. Sensor calibration. Potentiometer calibrates the sensor to the ramp using a physical device such as a protractor. Force impact sensor. Drop objects onto the force sensor and track voltage spikes. Motor control. Track how voltage affects the velocity of the object ramp angle. Ultrasonic sensor. Place object at various distances and heights and record sensor accuracy.
Although our project is inspired by Angry Birds, our system has applications far beyond just entertainment. This type of physical and virtual hybrid setup can be used in education to help students better understand concepts like projectile motion, collision forces, and real-time data acquisition in a more hands-on way. Instead of just seeing equations on screen, users can physically interact with the system and immediately see how their actions affect the results. In industry, similar measurement systems are widely used for product testing, safety analysis, and equipment calibration. For example, engineers use impact and motion tracking sensors to test how materials react to forces during collisions, which is important in automotive crash testing and protective equipment design. These types of systems are also used in robotics and manufacturing to monitor movement accuracy, measurement of applied forces, and improve system reliability. By collecting real-time sensor data and displaying it digitally, engineers can analyze performance, identify design flaws, and optimize mechanical systems more efficiently.